Perfect. So Ryan, go ahead.
Okay. First, before I get started, could I just get a little reaction from people? Who here is familiar with machine learning and neural networks already? Let's see. I guess I can't see since I'm sharing my screen. Arup, could you just tell me how many people are giving reactions? I can see it now. Okay, cool. So we looks like about half of you. Cool. Um, So I'm just going to be trying to give an intuitive overview today for those of you who don't know, and hopefully kind of give it in the context of our research, which is high performance computing research. And machine learning is increasingly becoming such a big part of that. And Arup and I have been working together on kind of an integration project with machine learning. So hopefully this is helpful. So to start, I'll just give a little bit of background about like what the task at hand is and what machine learning is useful for. So I'm sure all of you have taken an algorithms class, and for certain problems that are simple enough to simply use an algorithm for, um, that's before machine learning, that's all we had, and that's all we could do. That's the best we could do. And then for certain ones that are um, could be approximated. We could use those ones to improve efficiency. Um, but really, the scope of the types of problems that these traditional algorithms can solve are limited. And I will note here that, you know, um, one thing that I've seen lately and that is becoming a bigger thing is becoming reliant on machine learning or overusing machine learning for lots of problems. So I think one big thing to think about as you guys are solving problems in your education and careers is that if you can simplify a problem to not have to use machine learning for a solution, then that is almost always going to be better than using ML. However, there's a few issues I'll note about certain problems. First, of course, if it's too computationally complex and there's no good approximation algorithm, then that's an issue. Or if the scope or inputs are too complex, you can imagine a situation where, for example, I think image recognition is a big one where if you thought about how to try to, um, you know, classify an image, I'll get into an image classification example later. Um, it seems extremely daunting to be able to have some clear cut coded solution to do that. And then third is subjectivity. So a big thing that humans can do that computers are often not good at is have subjective opinions. So, for example, is this a four or a nine? There's um, I don't know. That it's up to for interpretation and people's opinions. So that's something that machine learning can do that traditional algorithms could never do. So, of course, the solution with machine learning is to throw a ton of data at it and hope that we can somehow improve a machine learning mechanism and make it better at doing a specific task. And I'll mention the two types briefly, or the two high level types of machine learning. And our focus for today will be supervised learning. And that's when the training data is labeled. So, for example, if suppose it's a nine, we'd give a bunch of inputs of images like this with the label that should be a nine, and then over time, with enough training, the model can get better at being able to classify that because it knows the labels of what the inputs are. And then unsupervised training is a little more complicated, and I won't get into the details of it today, but it's more aimed to discover certain patterns without needing labeled data. An advantage of not needing the labels is you don't need humans to go and verify certain data and labels, and because that's often a bottleneck for machine learning input data. And for generative AI, this is a big thing. I think modern generative AI uses a combination of both supervised and unsupervised, but for just the sheer volume that stuff like ChatGPT needs to be effective, it needs to see way more data than humans have time to classify. So I'll get into the details of a neural network for the purposes of supervised learning for now. I think I
Uh,
remember.
Hey, Ryan,
Yeah, go ahead.
sorry to
Sure.
interrupt you. Could you please hold on a bit? I want to add something here so that, as most
Sure.
of the
Yeah.
people are very new on machine learning. So, could you please go a bit to the previous slide? Previous slide,
Sure.
yeah. Okay, I just want to give you an idea, like, how you can visualize the problem. Think about it, okay? Think about it. Ryan is giving you a lesson about how machine learning works. So Ryan is saying that, okay, this is machine learning has two types. One is supervised and another is unsupervised, right? And you guys are knowing that, okay, machine learning has two types. So it is some kind of leveling data. Or think about that image, okay? For example, there are thousands of images, and that type of image, probably 80% of that type of image is leveled as 9, and probably 20% of that image is leveled as 4. Okay. Now, just think about like your brain. Think about that's a machine, and that brain is supposed to perceive the input from the data, like that 80% of the data is considered as 9, and 20% of the data is considered as like 4. So that is some kind of supervised learning, because your brain is getting all the knowledge by uh, by the input from the other person, right? And now think about that. Let's say um, you are you are observing some kind of arts, and people have some paintings, to be specific, like, okay, there are different people, that different people have different interpretation. One person might think about of a specific art, uh, the idea of that person might be different than others. Different people can perceive that specific art differently, so there is no specific label data, right? That is unsupervised. And there are a lot of different software, like you guys definitely use ChatGPT. It's basically unsupervised based on your input. It has like millions of, not millions, I should say, like billions or trillions of parameters to like to understand the specific question that you ask. So if you want to understand very clearly, just think about how you will learn. What is the process of your learning? You're taking different classes, you're talking with people, you're watching movies, videos, you read papers, you read poetry, you read different poems. So how you learn? So the people from different background are trying to incorporate these ideas and basically classify all different kind of learning techniques into here Ryan just said basically supervised and unsupervised. There is also another type of learning which is called semi-supervised and transfer learning. And there are different types of new ideas that different researchers have introduced. But let's focus today, like two types of uh, you know machine learning here. Okay, sorry for a long additions.
Yeah, no
Um,
worries. Thank you for that, Aruf. That was helpful, I think. And I think one thing I'll add to the unsupervised side of things is just for a little bit more context. One use case for this is something called clustering. So if you think about, suppose you give a computer a bunch of images, and you want to ask it which of these are similar. then you can imagine how that it might be able to pick up on certain patterns in certain images where certain pixels close to each other are have certain values or something like that without actually needing the labels. If you have a bunch of pictures of dogs, which are similar in some ways, some extremely complex ways, you wouldn't need to tell the computer necessarily that that's a dog, but it might be able to pick up on a certain pattern that since these two images it classifies two as similar, maybe you could group together all images of dogs. So just to give one potential use case, because I think unsupervised learning is a pretty daunting concept, and it's very complex, but hopefully that helps. So next, I'll just talk at a high level about neural networks, which is the mechanism behind machine learning. And simply put, I think it was a bit daunting at first to learn about neural networks, but for now, just think of it as a graph, as a directed graph where certain neurons connect to other neurons. And I'll get into the details of the connection in the future, but just for now, think about this structure where we have some input layer, so some variable number of inputs. This could be any number of inputs, and we could have any number of outputs as well. And the job of the neural network is to take some input and then perform some computations here in the middle. There could be several hidden layers for different purposes, and then come up with some values for the output neurons. And so essentially, you can just think of it as a function with multiple inputs and multiple outputs, or any number of inputs and outputs. And I think that that's a good way to think about it to start, as just a function rather than some otherworldly thing that often people think it is. Because under the hood, it's really just a bunch of math. So yeah, I think I'll stop here. If anyone has any questions about the structure, feel free to ask. I'll get into more of the details of it all later. No questions? Okay, cool. So let's zoom into a single neuron to try to simplify things and answer the question of, what does the neural network actually do, and how does it get from an input to an output? So of course the values of each neuron of the input layer, and I'll be using an example of the digit classification in a minute. And suppose you just have some grid of pixels representing an image, and each pixel is represented by a 0 to 1 value, where 0 being black and 1 being white. I'll talk more about this later, but just to give you a picture of what types of numbers might be represented as an input and how you can represent an image as an input. That's just one idea to throw at you. And then for the input layer, you have all these input numbers, whatever the use case might be. And then for the next layer, what we call the activation of the neuron is computed by all these edges, which each neuron from one layer has an edge to every neuron in the next layer. So essentially, you can think about, this neuron right here is gaining information about the input from the previous neurons. And we have these weights that we multiply each of these activations by these weights, sum them up, and then add a certain bias. And you can think of the weights and biases as kind of sliding scales for how important this activation, this transformation is. And that's a key piece of the neural network structure, because these can be adjusted. And I'll talk about the training process later and how it's adjusted. But just keep that in mind that, these are adjusted, and the neural network is represented by all these edges with values that, transform an input to an output with this particular computation. And then I mentioned activation earlier, and what that means is just how likely the network thinks this outcome is. And in the middle layers, what an outcome really means can be a bit confusing, but when it reaches the output layer, then the outcome becomes a lot more clear because I'll say it in the context specifically of classification problems here, where the output layer represents it's like a multiple choice question, one of different choices, and each one will have a value, and that value will represent how likely the network thinks that that choice is the answer. So, and then another thing to mention is this function g here is kind of I would call it like a squish function. So if you have some huge value from all these multiplications, and say you have several layers, then to prevent that number from getting extremely large and to be able to kind of classify each number in the same range, you can squish it down, say to the 0, 1 range, one function to do that. It's called the sigmoid function, to just make it a little bit more manageable and easier to reason about. So now with those weights and biases out of the way, a little bit more details about the computation and why this makes sense. I think I might have mentioned this a bit in the previous slide, but so like one potential hope, like how to intuitively think about it.
Hey, Ryan. Oh, sorry to pause you again.
Sure.
Could you please go back to the previous slide? No, previous one. Yeah. I want to ask a question to everyone. What do you think about these function Z here, B plus and summation of AI and WI? Do you guys have any idea? Can anyone give us a thought about that? Forget about the bias, just summation of AI and WI. What is A and what is W? What do you think about that? And what we are doing here? Anyone? Or do you guys have any problem of understanding that term? What does that mean? Okay.
Colin might have raised his hand. Colin, did you have any thoughts?
Yeah, Rube, did you want us to answer the?
Yeah, I think he was just trying to check, to get a little knowledge check and make sure that everyone's following so far.
Yeah, it's really funny. It's really funny if you don't know. It's totally fun. I just want to understand and how you guys have.
Yeah, since every node in the previous layer connects to every node in the next layer, that summation is basically like the value of the node times the weight of that connection, and then like that. Correct me if I'm wrong, by the way. That summation is like what the associates with the node in the next layer.
Yes, I think you were right. We're basically doing matrix multiplications, right?
Right.
We have
yeah.
We are doing matrix multiplication and performing a summation on top of that. So and I here denotes that if it has a 2 layers of, let's say it has a 2 layers of neural network, then first layer of that neural network will denoted as like I equal to 1 is first layer. Then sometimes it represents something like A0, 1, 2. Then but in this picture it starts from 1. So 1, 2, 3, it will go from one layer to another layer. That's how it goes.
Yeah, and I hope that the next few slides hopefully will provide a little bit more information about this process. So yeah, a little bit more details about the computation and what's really going on when we zoom out and look at all of these computations happening. So one intuitive way to think about it is that each layer kind of gets closer to the answer we want, which in the digit case, when if say the digit is a 9, then we would want the activation for 1 through 8 to all be 0, and then the activation for 9 to be 1. That would be the exact right answer if the network was able to output that. So, and one way to think about it potentially is maybe the network can recognize certain pieces of digits in one layer and then put those pieces together in another layer, and then, you know, classify the digits after that. I think that's kind of maybe an intuitive way to think about one thing that the network might be doing. If it actually does that or not, you know, it depends on the implementation, and it's likely that it does not. But you can imagine certain things like that that the network could be picking up on from certain pixels. So hopefully that makes it make a little more sense. And then another way to think about this is that, so looking at the input layer, so for the input layer of this digit classification idea, with each input neuron only knows about its pixel, right? So it doesn't really have, it barely has any information. It has a tiny fraction of the information it would need to be able to classify the image. And even as a human, looking at just that one pixel gives us no information. So if you think about then the next layer has an edge from every neuron on that layer has an edge from every neuron in the previous layer. So now it has information about the whole input space at least, right? And then if you think about if there's a layer after that, that layer now continues to get compounding information about, so it continues to get more and more information about the input space, and hopefully kind of more accurate information as the weights and biases are hopefully adjusted to be reasonable values. So that's another way to think about it. And then in terms of the structure and designing a neural network, in general, more neurons are going to mean it has more capacity for complexity. If you think about, you know, humans and organisms, humans have some of the most neurons, and we have some of the most neurons in our brains of any other organism, and that's why we're the smartest. We're one of the smartest organisms. So you can kind of think of that intuitively in the neural network structure. And if there's more structure and more computations going on, there's just a higher ability for it to be successful on an extremely large input space. So the trade-off for that, of course, though, is that with a larger network, there's more computations and it takes longer to train. So that's a big trade-off that you need to analyze for machine learning development. And then, like Arup was saying before, I think the zoomed in image kind of gave you a picture of what happens on an individual level, but how it's actually computed is with matrix multiplication. So if we can, you know, vectorize these operations and perform these computations that way, it's going to be a lot faster. And we keep coming out. I think just recently an AI engine actually came up with a faster way for matrix multiplication. Kind of the idea that doing things in bulk is faster than doing them individually. So yeah, like I said, the digit classification example is one of the classic ones for machine learning. It's a fairly simple example, as daunting as it might seem to write a program to take in a bunch of pixels and try to figure out what digit it is. But a little more details about, you know, what the structure means. I think I said this before, that, you know, let's say 0 is black and 1 is white, and then, you know, maybe 0.5 is gray. So you have these sliding scales, and it's important for them to be continuous for the network to be able to accurately compute those activations, and then, you know, have continuous ranges at the end. So, and that's important for, I'll get into this later, but for the math behind it, having differentiable functions for gradient descent is important. So that's kind of why you need these continuous values. So, and like I said, you know, we have these 10 outputs, all these pixels are the inputs. It goes through the network, performing those computations I mentioned, and then at the end, the likelihood of each digit is represented by the activation of that neuron at the end. So let's see. Like I said before, yeah, the squish function, I think I mentioned everything in this slide so far. But just to reiterate that, you know, you can think about certain neurons being brighter than others. And, you know, as certain weights might be larger than others and biases might be larger, you can imagine, you know, the brightness kind of flowing through the network, where certain pixels might have a bigger effect than others. And eventually when you get to the output layer, the hope is that what the actual answer you want will be the brightest. So, and one thing to note here is that, you know, getting one answer, just going through the network once to compute one answer is generally pretty fast. But the thing that's really computationally expensive about machine learning is training and making the model better, because that requires, you know, usually thousands, millions of examples to be able to fine tune all those weights and biases to make it work. So that's what I'll get into next is the training. So it seemed, you know, again, a daunting task to actually be able to improve these, you know, for the image recognition, it's going to be thousands of different weights and biases. And, you know, it'll be, you know, thousands of inputs to one function that we need to go through and adjust all these weights and biases to actually make it better. So in general, at a high level, the answer is just lots and lots of training data, and there's lots of techniques you can use for effective training data. Variety is really important. So certain things that you might want to consider, just making sure every digit is hit many times for this example. And a common thing that's done is maybe blurring it a bit. So maybe make every neuron or every pixel a little bit brighter to make a certain digit a little less clear, just to hit different edge cases and make it better at being able to figure out which digit a never before seen image might be. So again, I'll reiterate that for supervised training, we have an input and an expected output for this case. So it'll be an image that's paired. It'll be a bunch of pairs of images and then the digit that the network expects. So, and this is normally determined manually. I think for this example, there's a lot of database data that can be used that was created just for this purpose. And of course, the thing that's missing here is when we use one training example, put it through the network, then, you know, how do we evaluate how well the network did? Like, we would like it to just be right every time, but, you know, is it better if it was close? You know, if it identified a 5, like say a 5, it identified a 5 as a 0.8% chance when it was a 5, but then it identified 6 as 0.6% chance, so or 0.6 for the value, then you can imagine how that is probably better than if it was a 5 and it identified the 5 neuron as 0. So we can do that with a cost function with what we call the forward step of training, which is putting those inputs through the network and then, you know, analyzing the activation of those output neurons. So here I have an example of a 7, right? Of course, we would want this activation of the 7 output neuron to be 1 and all others 0. That's the ideal case. That means the network performed perfectly. And a common cost function that is used is the squares of differences. So if the activation of 1 should be 0, so we can take the difference of the actual activation and 0, square it, and then sum up all those differences. And of course, this 7 should be 1 in this case. So hopefully that makes some sense about, I think it's fairly intuitive to think about the cost is, you know, what it should, like the difference of what it should have been to what it actually was. And Arup, do you think you could step in and, I'm not exactly sure why the squaring it is beneficial. Do you think you could speak to that?
How good squaring? It's not just squaring; it's called mean squaring error. Okay, mean square error. I think that should be the cost function, right?
Right.
So there are a lot of different activation functions. So see, there are two parts. First one is activation function. Why do you need activation function? Activation function based on the type of activation function. For example, there are different type of. One of the very popular is sigmoid, then ReLU, then TANIS. This activation function will give you non-linearity. Okay, what does that mean? Non-linearity. Non-linearity means like when you detect, when you classify a problem. Okay, this is a 7 or 3 or whatever it is. Okay, so based on the weighted matrix and the output from each layer, that sigmoid function will basically classify based on the input from the hidden layers of the last layers. Okay, so it should not be a linear graph. Okay, it can classify based on the output of the hidden layer. And the second part is the cost function. Why do we need the cost functions? We have to generate the error, right? We have to generate the error. Okay, see, this is 50% matching with, for example, 7. So how do we decide that for that specific input it is 50%? We have to use some cost functions. Okay, someone can call cost functions, some there are different names, objective functions, and there are different ways to calculate the cost. One is this squaring. Why do we need squaring? Why do we need to square um, uh, the error function? It's called mean square error. So you have to calculate the mean, then you have a generated output value and the predicted value and the level value, and then you have to basically get the difference, and then you have to perform the square. So that's why here a1 is the
Right.
predicted value, and 0 is the level value. Okay, so
Yeah, and I think that
why we are doing a squaring with this? We have to do a square, otherwise we will get negative values. So for example, it
well, I
can
mean, you could
be
always absolute difference to solve that issue. But I think now that I think of it, I think the squaring is designed to penalize outliers more. So if you have something that's really wrong, you want to increase the magnitude of that. I think that may be the idea behind it.
Yeah, but ultimately you have to how good the actual output is will be decided based on the probability of the detection, right? So think about that. For the last input S7 minus 1 square, right? So for example, if the value of S7 is 0, let's say if the value of S7 is 0, right? Then what will happen? Then it will be 0 minus 1, that is minus 1. So if we don't square it, then it will basically reduce the it will basically reduce the whole value, right? So that's not the intention. We have to take the error of every single predictions with a positive value. So that's and that's one way. Basically there can be lot of different ways.
Sure. Yeah. Okay. Thank you for that. We'll stick with this simple example, but I think the important thing to know here is that, you know, there's different ways to do it, but what's needed for effective trading is some cost function that takes the expected values and the actual values and compares them. And so that can get some value, which will help us for the next step, which is called back propagation. And this is what I talked about earlier about adjusting those weights and biases to allow the network to perform better. And in simple terms, what this means is, and what this is doing is minimizing the value of that cost function. So for some set of training data, we can run it through the network, get the cost, and then the hope is that over time, as we adjust those weights and biases, we can decrease that cost function, because the lower cost means in general that the network will perform better for more examples. So yeah, the back propagation, it's pretty complicated. There's a lot of math involved. You don't need to worry about the math for now, but I'll talk just briefly about the method for how we can determine what might make that cost function go down in the next slide. And it's called gradient descent. So think about just a simple graph like this. There's obviously going to be, and if we're talking about images, there's probably thousands of dimensions. So which is a little bit hard to think about mentally. But if you think about it just like this simple graph, 2D graph, then, and this is a cost function, then what can we do to try to minimize that cost function? And gradient descent is a calculus concept, and it's the process of kind of, you can think about it, taking little steps downhill to try to find a minimum. And as these steps, you can see as these steps go, they'll get smaller and smaller, with the hope of not overshooting that minimum and landing right in that valley, to be able to minimize the cost function. And that's essentially what's going on with back propagation. This gradient descent is finding the inputs, the weights and biases, which will minimize the cost function for that training data. So one thing to note here is that the global minimum would be, the optimal place for the model to, or the optimal position for the model, and that would, be the best performance we could likely get. But finding a global maximum, global minimum, it turns out, is extremely difficult, and it's not really feasible to do for machine learning. So in certain cases, a local minimum might be found. Maybe it's pretty good, like this one. Maybe it's pretty close to the global minimum, but it might be pretty far off, and that can be a reason why your network isn't performing as you had hoped it would. Cool. So that covers that. So I think that's most of what I have that I wanted to cover today. A few things just to recap about. So the neural network at a high level is a graph with a bunch of connections that represent a function. So with any number of inputs and any number of outputs. And important to note that it's a very useful tool. It can solve extremely complex problems, but it does come at a cost. Like I said in the first slide, traditional algorithms to solve these problems, if you can use those, that's going to be better than using a neural network, because it's going to be a lot faster and doesn't require training. But in those cases where it really is a complex problem and you need something, or it's extremely computationally expensive to solve, like an NP complete problem, then you can use a neural network to approximate what what the function should be to solve every instance of that problem. Going back to the supervised learning, so training table is labeled, digit classification, each image has a label for what it's supposed to be, and the network learns on the data that you have labeled that this should be this. So hopefully when it sees similar images, it can classify them correctly. Like I just mentioned, that it improves by adjusting each of those weights and biases. Remember, the weights are the connections of the edges. So from one layer to the next, there's a value that you multiply all those activations by and sum them up. And then the biases are just a value on each neuron about that can be adjusted. That's just a constant to add to that sum of the weights times the activations. Just an additional input you can that will allow for a little bit more flexibility about how the network performs. So that's kind of what I have today for neural networks. Hopefully it was helpful. Next time I discuss with Arup. So kind of relating to the project I've been working on lately is, distributed machine learning and connecting with Cylon. And if you're not familiar with Cylon yet, Cylon's a big project in this research group, and it's essentially a data frame that's highly parallelized. We attempt to just make it extremely fast to help with these large data processing tasks. And if you look at this image, of course, there's tons of pre-processing and cleaning tasks that are almost always needed for any sort of machine learning project. So that's where Cylon comes in. Cylon's doing this cleaning and pre-processing. And then one big hope for the project I'm working on is being able to seamlessly integrate it then with machine learning. So next time I'll talk a little bit about kind of what's going on with this project and give you a little bit more context of the link between machine learning and this high performance computing research that we're all going to be working on. Arup, if you have anything to add to that, I'm sure they'd love to hear it.
Sure. Before that, I think Asad has asked a question regarding, did you see his message? He has a question. Let me read it. This is when choosing layer sizes or neuron counts, is the process of primarily heuristic, relying on the trial and error, or there are established theoretical guidelines that inform these decisions?
That's a great question. Yeah, that's so one thing I mentioned kind of towards the beginning was a level of complexity. So one like very high level guideline is the more complex the problem, the more layers and neurons you're probably going to want. And I think, there's this would be a good thing to research. I haven't looked into it too much. I'm sure there are some heuristics you could find. And I think further, understanding of how the gradient descent and all the calculus is working would lead to insights about how big the network should be, and what the distribution of neurons should be. So I think kind of just continuing to gain an understanding of on a low level how everything is working can help with that. But I think it's also, that's a very difficult task since it's the process is so complex. That's kind of my thoughts on it.
I want to add here on top of that. So it depends in what level of complexity you're trying to solve. For example, think about that. Think about on image classification. Okay, so each hidden layer is basically used to detect the features. Now you can define what kind of features. If you want to detect, recognize whether that image is human or not, then based on that, you have to decide what are the features you will use to detect that. Okay. Now, for example, to detect an image, to detect an human in the image, what are the information you need? Okay. At first, you need to detect the ages, right? All the ages. Okay. Inside that image, is there any human shape is available or not? That can be one feature. Ages. Okay. And another feature can be like, detect the eyes, whether in that image is there any eye. How can you detect an eye? Obviously use the generated features like ages and other informations to detect that, okay, there is an eye. There can be another feature like, are you trying to detect the nose? So based on that, then you have to choose like how many layers of them, how many layers you need to use to construct the neural networks. For example, the first layer can be used to detect the ages. The second layer can be used to detect the eyes, nose, and other informations. And third layer can be detected as any overlapping object. For example, like whether that human is riding on the bike or not. Probably that can be one information. Whether any overlapping object are there or not. So these are the features that you have to define before constructing the neural network. Also, did you get my point? Do you guys have any question regarding that? Okay. The second question is like, how to factor like the complexity of the task, nature of the input data. Obviously, I just said that uh, you know based on the input size and the number of features, that will basically add you additional complexity, and that will basically help you to design uh, how many layers the new neural network would be. It's totally based on the problem. Okay, detecting any digit is totally different than like recognizing a human in the MS. So
Yeah, I agree. And I think one other thing I'll add is like you said, or one thing you mentioned, Assad, is that um, potentially using trial and error. I think trial and error is also a big part of it in my experience, especially for people. I think people who have gotten PhDs in machine learning, in um, neural network training and those topics, I think are likely, equipped to make some of these decisions more accurately. But at our level and kind of when we're just getting started with machine learning, I think trial and error is an important piece of it. It can often, help you learn about what's going on. And I would say like my advice would be to just definitely, try those things like follow your intuition and try to understand why certain structures might work better than others.
yeah, Ryan is totally right, and we have to do a lot of trial and error to basically get the best configurations of designing any system. For examples, let's say you have choose like I will use 6 features, and so that I will use 6 different hidden layers. That your assumptions and also hypothesis behind that might not be true. You have to do trial and error. Probably might have like trial and error to find the right feature combinations. Probably adding another layers of um, adding another hidden layers might give you a totally different problem, right? So yeah, trial and error is very, very important.
Cool. Yeah. I think the last thing I'll throw on here is just a few resources. I'll make sure to share these slides with everyone so you guys can look about it. I think Three Blue and Brown has some great videos on some more details about neural networks. And then the next step will be to, if to start coding it up and, tinkering with some code on your own is, I think, one of the best ways to learn. For Cylon and in our high performance computing research, our focus is on PyTorch right now. So I have a couple of PyTorch resources there for you guys to check out. And then, like I said, about the next thing that I'll probably be discussing, and a big focus of this research group is about the distributed computing aspect of it. So here I dropped a tutorial about that if you want to get ahead and learn some about that. It could be useful. So I would ask you if there's any other questions I can answer, I'd be happy to do that.
Before going to the question section segment, Ryan, could you please add all those training materials to the Excel file? You probably see that in the Excel file. I have added, different
Sure. Yeah.
reading materials. So the data storage ML pipeline is another, is another section. You can add all those URLs to that section.
Yeah.
And I would suggest, to everybody, you guys should check the Excel file, and I have created different sheet for each one of you. So the plan is basically whatever you learn in the session, you have to practice when you have times in a week. And whatever you learn, you have to put into that Excel file, some kind of update that what you have done in this week, what are the stuff you've learned. And I would suggest, take a simple example, image detection, digit detections, and see the code, try to understand it, and also, write it. What I do all the time, right? Even if I have the code, source code of any problem, I always try to re-implement it to basically, try to understand what is going on underlying all these layers of layers in the neural network. So I would suggest that, read all the materials and try to implement that. If you face any problem, you can send an email, we can have a discussions in the weekly meeting. Okay. Now, please, if you have any if you have any question, please just ask. No one has any questions. Interesting.
Lost connection there.
Any comments, thoughts?
It makes sense to me.
Alex, Alex, are you saying something?
Yeah, I just wanted to say that it made sense to me. Also, I guess this is wasn't a part of the presentation, but when you're doing the error, will we need to know like I remember there's a large chain derivative required when you're updating the weights and biases. Are we gonna get more to that part of updating the network?
So my opinion on it, we'll see. Arup, I see if you agree, but my opinion is that there's lots of frameworks that kind of abstract the math away from us, and since our research is primarily focused on the high performance computing side, I think that we probably won't get into that, and the machine learning will more be a black box for us, and we'll see how we can connect it to other tools.
Okay.
But I would suggest, if you want to learn the mathematics behind all the derivations, Even if you want to take any class regarding machine learning, even if it's undergrad or grad level, there will be a lot of different mathematics for selecting the hypothesis space, then input domain, although the distribution of the data sets, how we can make the model more non-linear. So there are a lot, there are a lot of different maths behind that. But we are not focusing every single maths. That's a totally different, scopes. I would highly suggest, if you have time, take machine learning undergrad class. Obviously, you have to take linear algebra. That's very calculus and linear algebra, statistics. These three classes are very important. If you did not take that, I would highly suggest that you should take this class. And obviously, for designing new machine learning algorithm is not the part of our research scope, but ultimately we have to incorporate the underlying machine learning pipeline. So it is good to have to know, what are the different, for example, different what it's called, different APIs for activation functions. It can be ReLU, it can be sigmoids. How we can use deep learning networks for let's say 3-dimensional data. The problem of this domain is already solved. There are APIs. People have worked on that days and nights and implement those stuffs. So the stuff that are already implemented and added into the framework, we'll not spend that. We'll not spend much time on that. We will use that to basically solve new problems. So that's the scope of our research. Okay. Are you clear, Alex?
Yeah, makes sense.
Okay.
When is our next meeting going to be?
Always look into the Excel file. The next meeting will be November 7, 5:15 p.m. Alex, I think it's.
Sorry, I'm having trouble understanding right now. Please try a little later.
That's my fault. Anyway.
You got to get Siri under control.
He was unbelievable. Anyway. So the next meeting will be on November 7 at 5:15 p.m. Alex Fatea will give an introduction about how slumps work. So Alex, are you there listening to us?
Yeah, I'm here.
Okay, perfect. So try to make it more hands-on. Obviously, you can add different comments and stuff into the presentation, and if you like to do some kind of Slurm script and show us how it works, that would be nice.
Okay, sounds good.
Okay, so Alex, could you please wait a bit after this meeting, because I want to discuss about that a bit, for 5 minutes.
Okay.
Okay, perfect. So I don't have any more questions, and also any more suggestion. I already told that. Look at the Excel file, SPC research. You will see bunch of different status updates, contents. Obviously, grab any contents, read it, watch the videos, implement it. This is the playtime. This semester will be the playtime. You will just play around different stuffs. Okay.
All right, sounds
Okay.
good. Thank you, everyone.
Okay, thank you, Brian. Thank you so much for the presentation. I really appreciate it. Okay, bye, guys. So, Alex,
you.
okay,
Thank you.
please wait for 5 minutes.
Thank you.
Okay.
I think you have a great weekend.
Okay. Hey, Alex, are you listening?
Yep.
Okay, perfect. So you said you worked last summer in Biocomplexity, right? You had an internship there, right?
So I've been researching for almost a year before. Yeah.
Yeah, perfect. So the reason for this meeting, obviously, as you already have idea about research and have done some stuff with the Biocomplexity Institute before, and obviously you know how Slurm works and other stuff. So there is a project ongoing. That project is basically we are trying to publish a paper, and I want to add you in this project. Okay.
Okay.
And for that, we already like design the stuff. I will share the papers that we already archive it.
Okay.
So when you submit that paper into any conference or journal, we will add you in that paper as the author.
Okay.
And the responsibility and the main task for this project will be like you need to perform a bunch of experiments.
Okay.
So I am sharing you the paper. So just read the paper briefly. And the experiment for this paper, like the idea that we proposed in this paper, we have already performed the experiments. But what we need is we need to compare those results to the current state of the arts.
Okay.
So that part we need, like execute different operations with pandas, NumPy, with different data sets.
I see.
So those are the stuff. So I will give you the scripts. Okay. I will give you the scripts. I will give you the link of the data sets. You need to perform it on Rivana. Do you have access to Rivana?
Yeah, I do.
Perfect. So Rivana. So that's the plan. So let me share you. So
Okay.
yeah, this is a very good opportunity for you to have your name.
Definitely.
Yeah. Okay.
Just a kind of a side question. Is this separate from the meeting that we just had?
Yes,
or will
it
this
is.
kind of okay.
Yeah, it is totally separate. Yeah.
Okay.
It's totally
Awesome.
separate. Because as there are a lot of different projects, and some projects are currently on shape, and we have to submit that paper to a
Yeah.
conference. And so we basically need those person who already have prior knowledge of certain
Yeah.
stuff, right?
Yeah,
So
that makes
that's why
sense.
I thought you had that.
Yeah.
That's why I just request you.
Okay.
So
Awesome.
yeah, perfect. So let me share you the data sets. So data sets, the Saron experiment suit. Just give me a minute. Let me. So how is everything? How is your class? How many classes did you take? That's a very good question. But
I'm really liking it now because I've pretty much finished all the required classes. So now I'm kind of just taking the elective classes that I want to take, like in computer science. So like I'm taking a machine learning class, I'm taking a programming languages class. So it's definitely a lot more enjoyable than some of those forced classes. But I think it's going good so far. And course selection for next semester is coming up next week. So I'm excited for that as well.
oh, perfect.
Yeah.
So okay, so let me share you. There you are. Okay. I just dropped a mail. scripts. Sorry about that. Just okay, perfect. So I just send the message to you.
Okay.
Okay. Yeah, perform like all the experiments. Obviously, my session will be read the paper, and you will not understand a lot of the stuff. That's totally fine.
Okay.
But try to get the basic idea of what we're trying to do. That's one thing. And second is check the GitHub repository, and there are a lot of different experiments. We have choose like the pandas one, and obviously check all the URL for the dataset. So we have to use those datasets, and along with that, we have to use the pandas, script to perform different operations. For example, join, scalar, sorting. Okay, you will
Okay, I
you will
see.
get it when you
Yeah.
look into them.
Okay. Awesome.
Okay, Alex. Yeah, thank you so much for helping
Of
us
course.
to perform that. I do have a lot of different tasks, and I have to do in parallel. So that's I
Yeah.
too.
I just have one quick question before what's the timeline for this? What kind of pieces do you expect when, and yeah.
Um, it it really depends on you. Like,
Okay.
if you put a bit effort and give us a timeline. For
Okay.
example, look all this stuff. For example, within let's say 2 or 3 days, and probably assess some of the stuff and how long it takes to perform it.
Okay. Sounds good.
Based on your availability and based on the time you have. Then just give me a date, okay? I can perform it within that
Okay.
day. That'll be
Sounds
fine.
good. Okay.
Okay.
Awesome.
Thank you,
Perfect.
Alex.
Thanks.
Thank you for joining this call and helping me.
Yep.
Bye.
Of
Take
course.
care.
All right. Bye-bye.
And obviously, after doing that, I will add you in that project meeting. It's a totally different, schedule.
Oh, okay.
Then I will add you,
Oh, okay.
okay.
Yes. Yes.
Alex Fateh is the guy who did the stuff. Okay.
Okay. Makes sense. Great.
Sure. Okay.
All right. Thank you. Bye-bye.
Mhm. Okay.